Good afternoon, everyone. Thank you for taking out the time and being part of this session. The session is on instrumented analysis of gait and balance and the recent advances in the domain. So this is hosted by GITAM School of Physiotherapy. GITAM deemed to be university has been in the area of education for 41 years and with good student strength and number of programs being offered. Myself, today, I'll be moderating this session. Myself, I'm Dr. Ranganath. I'm an associate professor in GITAM School of Physiotherapy, GITAM deemed to be university, Visakhapatnam. My area of specialization is musculoskeletal sciences, and I work on manual therapy and sports rehabilitation. Here we have Dr. Michalina from University of Józef University of Physical Education in Warsaw. She is here on as an Erasmus Plus program faculty. She's an MSc in maths as well as in physical education and has PhD degree in biomechanics. She has a vast experience in biomechanics, has been working in the field, in the lab for more than 10 years. Her research interests include exploring the use of simulation techniques with particular emphasis on musculoskeletal modeling to advance the understanding of human movements. She also started working on entropy and factorials and postural control to understand the complexities involved in it. So with this introduction, I open the session for Dr. Michalina to go ahead.
Thank you for nice introduction. 1 second, I will share the screen. Do you see my screen?
Yes, yes.
Okay, thank you. So thank you once again for the introduction. Today I will speak about. This is the slide what you saw before, and I would like to say a few things once again because my pronunciation will be different. So I think that it will be nice that you will hear Polish pronunciation. My name is Michalina Błażkiewicz. I am an associate professor at the Józef Piłsudski University of Physical Education. Sorry, I would like to. 1 second. Do you know how to stop this thing? Yeah, stop sharing. Stop sharing. But I don't want to stop sharing my screen. No. 1 second. Sorry for that. Okay. Okay. I am an associate professor at the Józef Piłsudski University of Physical Education in Poland. And first I started my adventure with mathematics in the Warsaw University. And after I had possibility to study in Józef Piłsudski University of Physical Education, and I have master's degree in both because in Poland this is possible. If you are good, this is possible to do 2 master's degree in different universities. And after that, I wanted to combine my knowledge from mathematics and my knowledge from physical education. That's why I decided to join classes and knowledge from biomechanics. And now I still play with biomechanics and I use mainly musculoskeletal modeling to understand human motion. And also from 2 years, I started to join nonlinear methods to assess complexity of postural control. So I arrived from Poland, which is in green in the slide, to your country. So I don't know. But I still have the. Okay, sorry for technical problems, but as you know, probably all the time there are the technical problems. So as you see in the slide, I arrived from Poland, which is in green on the map, to India, which is in yellow, and it took me something like 19 hours. In the picture, you see Warsaw, the city where I live, and this is the view of my university. And my university was created in 1929 by Józef Piłsudski. And that's why we don't call this university of Józef Piłsudski, but we call this university of the name Józef Piłsudski because this is his property. And today I would like to say a few words about Gait. After I will start to describe a data collection and OpenSim software, and I will show you how I use it to characterize persons with drop foot, especially their gait. And I will show a description of muscle force distribution and mechanical power. After that, I will introduce you to the balance, and I will describe reaction strategy in response to anterior, posterior perturbations during gait. So let's start from general description of a gait, because if someone doesn't know or doesn't remember, I think that it will be a good point to start. So first, I would like to say that walking is one of the basic human movement, and it is also most frequent assess activity in order to identify possible dysfunction. So gait disorders can result in disability that can reduce life of quality. And as you probably know, gait is a cycle movement activity, which is repetitive. That's why it's also nice subject to assess. And gait is also defined like lost and regarding of balance in the alternation phases of support and transfer. So in this slide, you can see 3 types of parameters which are mainly assessed during walking. So we can assess kinematics parameters, which will be angles or for example, position of the joints during movement. We can assess spatiotemporal parameters and kinetics, which will deal with forces. And before I will start to speak about these parameters, I would like to say you what is a gait cycle. So gait cycle covers all of the steps and movements in between the contact of the heel with the ground and its repeated contact. So if we see in this slide the green leg starts with the heel, first contact, so this is the beginning of gait cycle. And after, if once again the same leg touch the floor, it will be end of the gait cycle. And each gait cycle is composed by two phases, two main phases, stance and swing phase. So stance phase normally takes 60% of gait cycle and swing only 40%. Of course, if we start to walk faster, the stance phase will be shorter. If we walk very, very slow, the stance phase will be longer. That's why you can observe, especially in elderly population, that they walk very slow because it is safer, because their stance phase is longer. So their balance is longer and the gait, as I said before, is safer. And of course, during gait cycle, you can detect also two double support phases, which take only 10% of gait cycle each one. And they are on the beginning of the stance phase and on the end of the stance phase. And double support phase is when both legs have the contact with the floor. And according to Perry, Jacqueline Perry, you can see this division of gait cycle. So apart that we know stance and swing phase, we have also a lot of another phases. So we have initial contact, which take only 2% of gait cycle. And this phase includes the movement when the foot contact the ground. And this is somehow like initial stick with the ground. And in here we have first time the absorption of the forces when we start the shock absorption when we start the motion. Loading response is the second phase, and in here we can observe knee flexion, which help us to absorb whole forces which were created before. Next, we have middle stance, and here whole foot is in the ground, and terminal stance when another foot will go forward. Press swing is the preparation for the swing phase, and three phases of swing, initial, mid, and terminal, there are only somehow passive phases, because we have to go with the leg from backward, to the mid and to the forward position to start second gait cycle. So what gait parameters we have? We have spatial temporal gait parameters, and I can say basic parameters which serve to assess gait. And in between we have space parameters, time parameters, and speed parameters. So if you look at the space parameters, we have few of them. First is step length. Step length is distance between corresponding successive points of heel contact of the opposite foot. So it's, as you see, from one heel up to heel of another leg. So this is the step length. Stride length is simply the same like gait cycle. Step width is defined like lateral distance between both heels while stance phase. So during, better saying, the double support. So if both feet are on the floor, we can measure step width, and it's between the distance of the heels. And the last one is foot angle. Foot angle is defined like an angle between the line of progression of the body, which is in here, dot line, and the longitudinal axis of the foot, which you can find in here. So this is space parameters and basic description of the gait, the most simple. Next, we can find time parameters, and it will be stride time, step time, stance time, single support time, double support time, swing time, everything what we can measure using time. And the last one, speed parameters, cadence and walking speed. And cadence is number of steps per minute. And what I said before, if your gait is faster, as you can see in here, the stance phase will be shorter. So this is very important to remember, especially when you work with disabled persons, that their movement can be very slow because they don't have good muscle forces or good control, or simply they are afraid, or because this slow gait will be safe for them because of this, what I said before. There are also a few factors which affect gaits. As you can imagine, this is age, what we saw, gender, size and shape of bone components, distribution of mass in body segments, joint mobility, muscle forces, type of clothing and footwear, habits, physical structure. So that are a lot of components which can influence gait. But the good thing is that if we are healthy, our gait is very similar, and this you will see later in my presentation. So now I would like to go to kinematics parameters, mainly to angles. And this slide is very important because you have understand how biomechanics define the angles. This is not so simple because this is not simple, let's say, angle between the segments. So the angle, what defined motion capture system, because they are using in biomechanics, these angles are defined like angle between the long axis of the proximal segment and the long axis of the distal segment. So if we look at the knee, this angle will be in here. So you can imagine that in knee joint, in healthy person, we never will go to zero position. Quite never. We will be near, but our extension will be 5 degrees, maybe 5 degrees in healthy person. Never zero. If zero, it means that there is hyperextension. So we have to be careful about it. And how motion capture system calculates angle. Why I speak about it? Because after you will see curves what are presented during walking for ankle, knee, and the hip. So in here, according to Winter, which was very famous in biomechanics, we can see segmental angles, which are on your left. And this is the segment position according to the horizontal line. And we can define the angle for foot, for leg, for thigh, for trunk. And here we have on the right side joint angles, which are defined as I said before. And there is nice connection between these two angles, and you can see them in here. So this is the connection. So hip angle can be calculated like angle of the thigh minus angle for the trunk. Knee angle is angle for the thigh minus angle for leg. And this is what motion capture system do. And this is what biomechanics understand under under angles during walking. So let's see how the angles looks like. This is, according to Perry, the gait, the curve during gait cycle. This is ankle curve. This is the knee curve. So you can see in here that mainly here we have a flexion, as I said before, and extension will be minus. In healthy person, we don't find this extension. We will be near there. And in here, I have to mention that this black line is a mean, and the dot line is a standard deviation. So what you see in here, this is the mean curve in the healthy population, and this is standard deviation. So if you go to the lab, and you measure your walking gait, you assess your curve should be somewhere between this dot line. If it will be, this means that your gait is okay, that there is not this alternation because of something. And if you have to look at the hip, this is a hip joint. Sometimes persons would like to see if our gait is some kind like repetition, if we repeat the same pattern during few gait cycles. And for this, persons normally use angle diagrams, so cyclogram. And in here, you see on x-axis joint, hip joint angle, and in y-axis knee joint angle. And if you have a lot of gait cycles, it will look in this way. So you can see if your cyclogram is some kind like repetition. If no, like in here, it means that something happened, and you have to know why. Because this was the end, because the velocity was lower. It will depend all the time on the task. So the main popular, let's say, graphs of the joint, of the angle, are these three: ankle, knee, and hip. Now I would like to start to speak about kinetics parameters. So in kinetics parameters, we will speak about ground traction forces, torques, and powers. As I said, we had briefly introduction to spatiotemporal parameters, now to kinematics parameters, so to angles. And now it's time for kinetics parameters. Kinetics parameters will appear thanks for Newton's third law of motion. So forces always come in pairs. You push on a wall, the wall pushes on you. This is action, reaction. That's why if we look at the ground reaction force, we will see reaction on how we act on the ground. And let's see in here how what's happened with ground reaction force. So what we will see during measurements, because measurements of ground reaction forces are done using plates. If you use the plates, normally you will see resultant ground reaction force. You can see also the components, but if you see only the resultant, you have to remember that in 2D space, you will have components in 2D. Now I will show 2D space. So we will have the horizontal component and we will have the vertical component. If we are in 3D, because we are in 3D space, we will have also the mediolateral components. So in here, you can see the print screen of what we see during motion capture analysis. These are the resultant ground reaction forces. And we can see that if we divided this vector to vertical and to horizontal one on this leg, you will see that in here we will have horizontal components. What doesn't mean? This means that here we will have deceleration for this leg. Why? Because the component will be in opposite way of our motion. And here, of course, we will have the vertical component which act only upwards. If we look at the second leg in here, we will do the same algorithm. So we will add the horizontal component, which will be in the same direction of the motion. So you can imagine that in here we will have the acceleration of the leg. And it's true because this leg is preparing now for the swing phase. This is the pre-swing, so in few seconds, this subject will have the initial swing phase. And as I said before, the vertical component will act upward. So in here, you can see the typical vertical component during walking. And on the horizontal axis, you have gait cycle. So you can see that only during the stance phase, you have the ground reaction force. In here, all the time, you have two max peaks and one mean. Two max peaks all the time are 120% of body weight, not body mass, body weight, because body weight will be in newtons, body mass in kilograms. We are speaking about the forces, so we cannot speak about kilograms. And minimum, it will be 80% of gait cycle. So in here, it's an example on your right side. If we have a person whose body mass is 50 kilograms, it means that the body weight of this person is 50 newtons around, because I assume that the ground velocity is 10. So two maximum peaks will be 120% multiplication 500 newtons. And minimum the same, but 80% multiplication 500 newton. You will ask me why? Because during walking, we don't change our weight. if I am 70 kilos, I will be 70 kilos all the time. But why we have these 20% of the changes? Because exist interior forces. Interior forces are connected with the acceleration of our body. That's why we have these changes. And second component is, of course, anterior-posterior component, which will inform us if there was the acceleration of deceleration of the body. So as you know, in the first phases of gait, so initial swing, initial contact, loading response, mid stance, we will have the acceleration of our body because we a little bit stop to absorb shock after first contact with the ground. And next, to be prepared for swing phase, we have to accelerate. We have to accelerate. That's why we have here plus. So two peaks are on 20% of our body weight. This is typical graph of the anterior-posterior component of ground traction force. And mediolateral, normally in the analysis, person doesn't take it a lot under consideration because it doesn't give you a lot of information because it's very unregular. So it's only 5% of gait cycle, and no one takes this component when try to assess gait analysis. And this what I show until now, it's typical gait without the persons without disease. This is important because this is your, let's say, normalized data. It's something like a standard. If you have standard, and if you have one person with disease, it will mean that simply you can compare and you will see where the differences are. So during gait or during another activity, it's very good to have some standards, because you will see how far from the standards you are, and especially in rehabilitation, because if you see, for example, that here was something wrong, you can help to this person. You will know which muscle work in this moment, so you can help. And in here, I have some problem. Do you hear me?
Yes, Michalina, we can hear you. Please go ahead. Yes. Yes, Michalina, we can hear you.
Do you hear me?
Yes, yes. We can hear you, Michalina.
Okay, so can I go forward?
Yeah, of course, yes.
Okay, so now I would like to speak about Gateline. I would like to speak about Gateline. Gateline is the gives us the information when the center of pressure, it's a visual expression of the part of gait during which the foot is in contact with the ground. So normally first we start with the heel. After whole foot and after the end of the foot. And if we look at the picture of the foot, it is in this way. So the red line will, red zone will show us that in here the pressure is very high. And at the end of the gait cycle, big toe is the finishing of the gait, of the phase when the gaits finish. So the gait line is the points when the ground reaction force, resultant ground reaction force, are put. And this is how it looks like in healthy persons. So if you one time will have possibility to join zebra's path length, you can assess the pressure under the feet. And you can assess if some person has, for example, flat feet or where the big pressure is. And remember that red zones means that the pressure was really, really high. And the blue one means that the pressure was very low. And in here you can see the print screen from zebras, and you see the foot during gait. So first we load heel, after we load the big toe. This is how the gait line looks like. And if we have some deformation of the foot, it will be, of course, different gait line, different loadings. Let's go to the muscle torques. Let's go to the muscle torques, and muscle torques will inform us, especially what was the loading during gait. And the convention for moments is shown on the left. Count clockwise moment acting on the distal segment from the joint are positive, and clockwise moment are negative. So the plantar flexor moment is negative, the knee extensor moment is positive, and the hip extensor moment is negative. And once again, you can see in here, according to Perry, how in biomechanics the joint torques curve looks like. This is the ankle joint torque during walking. This is the knee joint torque, and this is the hip joint torque. And of course, you can accept which muscle will be the most active during each phases. So now I will go to most important thing of biomechanics. So to the inverse dynamic task. Because we already know how the angles during walking look like. We already know how the torques look like. And I mean that it's very good to understand how we can calculate what is inside. And of course, joint angle will appear if we will have the devices, the motion capture device. So if we have a person and this person will come to the lab, we will prepare these persons and we will measure the position of the joints using normal video camera, or if we have using some motion capture system. So if we use a motion capture system, we will have markers put it on the joints. If yes, you have to remember that whole motion will be during the time, in the time? If yes, we can calculate velocity. So we will have velocity of the segments, so of the markers. And if we had before the joints, we will have also angular velocity. If yes, this angular velocity and normal velocity are in the time, so we will have acceleration. Acceleration of the segments, of the markers, and of the and angular velocity of angles. Everything from here will go to dynamics equation of the motions. Also, what is needed in here, we need ground traction forces. It is very important to have ground traction forces. This also goes to dynamic equations. If yes, in here, we will calculate muscle torques and internal forces. This is the general scheme, like how we obtain muscle torques. How we obtain muscle torques, what I showed you before, And now is the time to go to OpenSim. Why? Because everything what I said until now, it's experiment. So it is experiment. You can measure it. If you have 4 plates, forces plate, if you have motion capture system, you can measure. And it's good because in very fast way, you can compare persons with disabled with the persons who are healthy. And you can detect the places where is wrong, where is the problem. But there is a unique thing what you cannot measure. This unique thing what you cannot measure is muscle forces. Muscle forces you cannot measure. You can only assess muscle activity. You can only assess muscle activity. So let's go to the OpenSim. OpenSim is a free open source software that allows to build, analyze computer models of the musculoskeletal system and dynamic simulation of the movement. It was released on August 2007 by Stanford University in US. Its goal is to provide free and available tools for biomechanical research. Users can explore and can build also their own models and they can play with the models to assess the motion. So you can do everything in there. If you don't have motion captures, there are already models with the data and you can modify the data. And it's just that you will give the question and you can try to answer using this question. So what models we have in OpenSim? So we have 2 main models, Gait 2354 and Gait 2392. What is the difference? Difference will be in the muscles. So how many muscles we have in the model? So in Gait 2354, we will have 54 muscles, and in next model, 92 muscles. And you have to remember that in these models, we will have mainly muscles who act on lower limb. And 23, it means that we will have 23 degrees of the freedom. And on your right side is definition, and you can find the definition of the joints. So for example, in here, the knee joint has only 1 degree of freedom, and the ankle joint has only 2 degrees of the freedom. Hip joint, 3 degrees of the freedom, and pelvis is connected with the trunk, also with the joints of 3 degrees of the freedom. And you have to remember that this is a model. If we have the model, it all the time will be some simplification of the reality. Never ever very good, but if it's good enough to answer to our question, and if it's good enough to model reality, and the answer is not far away from the reality, it will mean that model is good. It's still something better than nothing, because we cannot measure. So if you cannot measure something, modeling will appear in this moment. And here you can see which type of the muscles we have inside of the models. So we will have Gateline 2003 muscles. I mean, this is the name of the model of the muscles, but based on the heel model. So this is heel model of the muscle. And there are few parameters which are exactly known because from the anatomy, like pennation angle, like maximum contraction velocity, like optimal muscle fiber length, muscle isometric force. This is already in the model. This is put it in the model. What is good that you don't have to search it in the papers. This is already in. So now I would like to present you whole steps what you have to do in OpenSim to detect the muscle forces. Because as I said on the beginning, the aim of the OpenSim or anybody, because there is also commercial software, anybody who works in the same way like OpenSim. So the main aim of OpenSim is calculation of the muscle forces, which you cannot measure. You can assess only muscle activity using EMG. Activity and force, there are different things. And here, it's the scheme what you can follow during playing with OpenSim. So first, we have to choose our model. And after, we have to scale this model. After, we will do inverse kinematics to have joints angle. After, in reduction residual algorithm, we will play to don't have errors. And after that, we will go to computed muscle control to have our muscle forces. So this is general way to see, but let's go slower to make you understand how it really works. So first we go to OpenSim and we choose model. You can have model with 54 muscles or model with 92 muscles, as I said on the beginning. What else? You have your subject. You have your subject, some person, and you have the data of this person from motion capture. So you have the position of the markers. So you have the position of the markers. So in scaling, you will have virtual markers, which are on the model already. And you have your experimental markers. from your motion capture system. And for scaling, you have to count the distance between the markers to measure in this way the length of the bones. And after that, you will have some value for this segment. And if you multiply this value by the model, you will have experimental, you will have your subject, yes? Because if you have virtual, you will count experimental, so S is experimental divided by model, you will have experimental. So you can scale your model. In here below, it's for two limbs. If you are symmetrical, you can use this one. If you are not, you have to go segment by segment. And in here, I know that it doesn't look nice, but this is the code what you can find in OpenSim, because it's, as I said, it's free software, so you can go inside and you can explore everything. And what about mass? Mass is scaled in the same proportion as it was in the OpenSim model, so in the generic model. Next, if we will do it, we can go to inverse kinematics. So first time we will have a motion. So the task of inverse kinematics is that experimental markers should match by model markers in the way that the angles will appear through the time, and the angles will be the same like in real world. So this is the walking gait. Here you have a markers, and you make a transition from this to your skeleton, and you will have an angles. Angles, what about I spoke on the beginning of this presentation. And next, you can go to the inverse dynamic section, because if we go, sorry, here, we have in here possibility to go to inverse dynamic section. And after that, we have residual reduction algorithm. This algorithm is done in order to cancel every errors. Because as you probably know, during experiment, during measurements, we will do a lot of errors because we are human. So after experimental, the third law, the first law of, the second, sorry, law of Newton will not match. And that's why there are small residual force which should be applied to the model to match this equation. And in OpenSim, they should be the smallest possible. So in this algorithm, we do everything to do this small, to have small residuals. And what we do, we only change the center of mass of the torus when the ground reaction forces are added in. If we will do it, we can simply go to next step, computed muscle control. Computed muscle control. And computed muscle control, it will help us to say which every single muscle has a force and how it works. It works using the static optimization task. So as you know, I mentioned it before, but now I will tell it better. Each muscle which is inside of the open seam is a model. So this muscle has some properties. This is the heel muscle model. And there are the properties, I mean, the relationship force and muscle length. As you can see, for passive part of the muscle and for the active part of the muscle. And passive part of the muscle is a tendon, which is in here, and active part of the muscle is the reaction between actina and myosina during contraction. So this is the main graph from biomechanics. And we have also in other dependencies, force and velocity. This is the heel curve. This is the heel curve. So these properties has to be inside of the model. And next, if you use the static optimization tool, we will need another data about the muscles. So everything what we can measure about the musculoskeletal system, about the geometry, everything what we know, we have to put in the model. So let's start him from the beginning, and let's start from the example of muscles which acts on the ankle, So you can imagine that if we have net ankle moment, for this will be responsible tibialis anterior extensor digitorum, so major flexors and major extensors of ankle joint. And you have to remember how the muscle torque curve looked like. I mentioned about this curve on the beginning. And if we go forward, because still our question is, what is the force of tibialis anterior? What is the force of extensor digitorum, and so on. So if we go forward, we can write that moment generated by ankle joint in here should be equal as torques from extensor minus torques from flexor, because they act in the opposite way. So in this example, what we have on the slide, we can go forward and we can write this equation. So we have to only remember what is a torque. So torque is simply multiplication of the force and the arm. So for extensors, we will have muscle moment of ankle will be equal force of tibialis anterior, multiplication bar its arm, plus force generated by extensor digitorum, multiplication bar its arm, minus this what will play in opposite way. Don't worry if here it will be change of the sign. It doesn't matter. It doesn't matter. It's very important that here it will be the minus as a sign that these muscles are opposite function to those muscles. And next, we have to think what we exactly have in the equation. What data do we have? So first, we have the arms. We have the arms. So how long from the ankle joint is the initial point of the muscle? We will have it from example, from pictures, from tomography. And we will have also this, so net ankle moment, because we will have it from our motion capture system. And what we don't have? We don't have muscle forces. So you will see that we have only one equation with, in this case, 1, 2, 3, 4, 5, with 5 unknowns. So this is disaster because everyone knows that we cannot resolve it. But we have something else. We have something else. I mean that we have the limitation. That we have limitation of forces of these muscles. Because, for example, muscles tibialis anterior cannot extend 900 newtons. Extensor digitorum, 800 newtons. So we have this limitation. And if we have this, we can simply calculate the muscle forces. It also is some criteria. And this criteria is to minimize muscle stress, metabolic energy, or muscle activation. This is the minimalization. And from here, you will have this maximal isometric force. This was done, this table is done from, for example, DELP. This is from DELP, here. This is from DELP. This is from CART. It was done by experiment. So we can say that these values cannot be extended. And from this calculation, we cannot do it manually because it will take a lot of time, but anybody will do it. Anybody will do it. Of course, you have to wait for the results, sometimes half an hour, sometimes 10 minutes, it depends, but you will have muscle forces distribution. And now I would like to show you Gait persons with drop foot. So I would like to show you evaluation of muscle forces distribution during Gait of these subjects. This is what I did a few years ago, and this is exactly how I used OpenSim. So first, we have to know what doesn't mean that gait of persons with drop foot. So drop foot is the inability to lift the front part of the foot due to the weakness of dorsiflexors muscles. So they are weak and simply person cannot up the feet. And what are the causes? First, it will be nerve injury. It is the most common. Next, brain or spinal cord disease. So for example, stroke, cerebral palsy, Charlotte-Mason tooth disease, or muscle disorders. So for example, muscular dystrophy or polio. This will be the cause of drop foot, the most common one. And consequence, it will be different muscle force distribution, simply different than the muscle force distribution in healthy subjects. And we have the theory that when a muscle of the musculoskeletal system is damaged, other muscles tend to compensate for the loss of injured muscles by applying extra effort. So we have two ways. First way is by modifying the effort of other muscles while still performing the same motion as a whole, or by modifying the motion into another one that naturally results in a lower mechanical load was imposed of damage matrices. So the question is, what disabled person will choose? Or disabled person will try to walk as a healthy person and will modify effort and maybe will destroy healthy joints, or maybe the motion will be different, but in the same time, it will be more natural for this disease. So the aim of this study was to analyze the muscle force distribution and compensation during gait persons with drop foot. We had 10 persons with drop foot and 10 controls. You can see, simply you can see here the persons with drop foot and typical gait. I don't know why it doesn't, it's working now. So on the slide you can see on the left drop foot gait, and on the right typical gait. And what you can see that drop foot gait starts from the toes because the dorsiflexors muscles are weak. And what we can observe that we have hyperextension of the knees because dorsiflexors are also weak. And also we will have different behavior in the hip. So what we did, we simply took the kinematics and kinetics parameters using Vicon system and Kistler plates. So from Vicon system, from cameras, I had kinematics parameters. Because it was connected with Kistler plates, I had kinetics parameters. And whole data, what I had, so the marker's position and ground reaction force, I had from the system and I put it in OpenSim. I went through skill, through inverse kinematics, reduction residual algorithm, and computed muscle control. Person by person, so 20 simulation because 10 healthy persons and 10 persons with drop foot. This will be maybe interesting for you. This is our lab. This is our lab. So in here you will see cameras. They are in here. Next, here we have equipment to measure isometric force. But it was not the case in this study. And here you can see the 3 Kistler plates. So persons while walking, this was the direction of walking. Here it's another view for Kistler plates. We call them 2 news plates, and this is the old one plate, but it's only the picture. And here there are computer for Vicon system. So in here you can see also the picture of flower lab from another view. And as you remember, we had in this case model with 92 muscles, and in this model weak muscles were 6. So peroneus longus, peroneus brevis, tertius, tibialis anterior, extensor digitorum, extensor hallucis. There were dorsiflexors in OpenSim. Not all of them, okay, because peroneus is not only dorsiflexors, but these were response for drop foot. And in here, you can see the difference in kinematics and kinematics parameters between drop foot group and control group. So in red, you have healthy subjects. These lines are the means across 10 subjects. So C was a control group, and this was red line, and black line was drop foot group. And you can see where the difference appears. So for ankle joint, for angle, you have in initial contact and loading response, as we was expected. In the knees, quite whole stance phase, and also something in the hip. If we look at the kinetics parameters, here we have torques, ankle, knee, and the hip. We see the difference in the initial contact loading response for torques, and we know it because already we know that the muscle doesn't work. But we can see how big differences it was. And unfortunately, we have to remember that our body is a chain. So if something doesn't work in one joint, probably it will appear some problem in other. So you, as a future physiotherapist, you have to remember that you cannot play only with one joint. You have to look at the person as a whole, not only one joint, not only where is the problem, but whole body. And because as you see in here, the biggest problem started to be on the knee. This is a difference. You saw it on the film, but you didn't expect that the difference in the moments, so probably in the force, will be so huge. And in here, you can see our results. So weak dorsiflexors muscles, because we have here newtons. So this is the result already from OpenSim. So in red, it is a control group, and in black, drop foot group. So for weak muscles, we have the biggest differences in loading response and in whole swing phase. So as physiotherapists, you have to remember which muscle and how they work during these phases, because in here we have the biggest problem. And what we did in the next, to see how this weak muscle can be compensated, we calculated the area under the muscle forces curves where during the gait cycle for each muscle. And according to formula, what you see in here. So this was the formula and this was the question. So we asked how much and in which muscle surface area increase in dorsiflexors group compared with control group. So where are the differences? And this is the response. So if you look at the area, because remember that it's not clear force, this is the area. The bigger differences between area is, the bigger problem on compensation appear. Let's first see the results for weak muscles. Weakness of 6 individual muscles led to change in forces pattern of many other muscles through the leg. And here you see that in each muscle, control group had bigger area. And the biggest area was for tibialis anterior, the biggest for tibialis anterior, because in control group, this area was 224% bigger than in dorsal drop foot group. This is what we can observe when we see in other muscles. So in here, we see how muscles, which muscle had bigger area in drop foot group. So flexor hallucis, 417% bigger area. So probably most bigger forces than flexor digitorum, tibialis posterior, semitendinosus, gastrocnemius, biceps femoris semitendinosus. So we can quickly go to the conclusions that in clinical situation, it's reasonable to assume that patients whose neuromuscular system has been damaged will choose performing the same or very similar motion as the one that was employed before the damage. This is the first. Lost in individual muscle force in the region of ankle joint are compensated by the increased force in other muscles acting on the joint. For example, tibialis posterior, flexor hallucis, and digitorum, and other muscles acting in the neighboring joints. Radically different motion involving unusual force that has to be exerted by the muscles can cause even greater damage to the body. For example, on the knee ligaments. So if some damage appear to our body, we have to remember that our body would like to compensate. If yes, there will be for sure some another forces, some unusual forces, which act on our body. And it can happen that are too big. So, for example, in the case of persons with drop foot, we saw the hyperextension of the knee. And in here, I would like to show you also how biarticular joint muscles act. So we chose posterior muscles, semitendinosus, biceps femoris, long head, and semimembranosus, and anterior, vastus lateralis, rectus femoris, vastus medialis, two groups. And it was result that if we have these posterior muscles, also the area under the curves, it is the mean area, this is the standard deviation, in persons with drop foot, which is black, and healthy persons, which is red. The difference was as much. So semitendinosus, the biggest differences, the biggest activity of this muscle, the biggest force of these muscles. And in here, we have what's happened with vastus lateralis, rectus femoris, and vastus medialis. Remember that black is a persons with drop foot. In here, we have difference between these two groups, and these muscles were stronger in the group of the healthy persons. Rectus femoris was stronger, 135% than persons with drop foot, but these were weaker. So in here, we have to be careful also about the muscles who cares about two joints. Sorry that you can see this in Polish language. And let's go to the power analysis during drop foot gait. So the aim of this study was to analyze the mechanical power redistribution during gait of healthy subjects and persons with drop foot. Just short remember that joint power is a product of joint moment and joint angular velocity, as you can see in here. And according to Winter, power is positive when the body generates mechanical energy through concentric muscle activity, and is negative when the body absorbs mechanical energy through eccentric muscle activity or elongation and soft tissue. So if you go in here, this is the picture from Winter book. And this is the power, ankle power during walking. It is normalized by kilogram, because if you normalize, it is easier to compare subject between them. And in here, A1 region is a negative power corresponding to eccentric plantar flexion activity at the ankle during mid stance and terminal stance. A region of positive power corresponds to concentric propulsive plantar flexor activity during press swing. And if we will remember this description, we will see in here the biggest differences between control, which are in red, and drop foot, which are in red. So in the region of positive power. So this was the concentric propulsive plantar flexion. Plantar flexion were most stronger in the, of course, in the persons in the controls. In here, the same we can observe for the knee, from the knee power. Here, normally, if you do the registration, you will have 4 regions and only one positive region, which will correspond to eccentric knee extensor activity during mid stance. This will be in here. In other regions, K1, K3, and 4 are negative and will all the time correspond to eccentric activity of muscles which are main active in those phases. And in here also we can see completely different power in persons with drop foot. Completely different power. Remember that the power is multiplication of the joint moment and joint angular velocity. So everything in here influence. Also that the persons with drop foot walked slower. And this is the mechanical power. And in here we can observe the power during walking from hip joint, and also only to 3 regions, small region of positive power H1, which corresponds to concentric hip extensors activity during loading response, and H2, H3. And the result we have mainly in region H2 and H3. I was expecting to have also the difference between those 2 regions, between H1, where the muscle on the beginning of the cycle, gait cycle will work in different way, but it wasn't. Remember that here we compare the area under the curve, yes, the area under the curve. In conclusion, significant source of energy generation are ankle plantar flexor muscles during push-off for both groups. Hip flexors worked concentrically to accelerate the leg forward in swing. Hip extensors working concentrically to accelerate the tide of the swing leg backward. Significant source of energy absorption. The remaining region H2 represent energy absorption. At the ankle joint, muscles act mainly as energy absorbs. So this is what was related to energy. And let's say that the last part of our adventure with persons with drop foot is what orthosis will do with the kinematics and kinetics parameters. So we put it as a treatment of drop foot. You can use exercises, you can use orthosis, some electoral functionality simulation or surgery. You have this possibility to save these persons, to save their weak dorsiflexors. And of course, the first thing is to do the exercise. But as you probably know, if you ask the person to do the exercise at home, they will not do it. They will not do it. Or they will do it not time to time, so they will be not regular. Electrical stimulation, you have to have some good equipment. Surgery, people don't like surgery and not all of them can have it. So the simplest thing, it will be to choose orthosis. And in here, the purpose was to find how this ankle foot orthosis will work and if it will help the person to improve kinetics parameters and maybe activity, in this moment activity of the muscle. So this is the drop foot gait on your left side, and this is the type of orthosis what we put. And this was only one subject. Why? Because when we had the contact with another persons, usually they said that they don't want to put orthosis because it's painful. So they didn't put, they preferred to walking in different pattern. But there was one man who had this type of orthosis. This is some thing like elastic. So it's good because you can do this elastic longer or shorter in this way that you maybe will not feel the pain or pain will be acceptable. So what we did the same scheme like before. So we used Vicon system and Kistler plates, but additionally we had also EMG. And EMG, we put it on these 8 muscles of the leg, which is weak. And after that, we had some very nice algorithm to compare the curves. That time I thought that it's very nice, but in this year, maybe 1 year before, I discovered better algorithm to make curve, to compare the curves. And about this, I will speak a little bit later. But going in here, from this work, Milanowski, we had to calculate two factors, F1 and F2. DF is drop foot, and AFO is drop this person, the result of this person with orthosis. And it results that if this first indices is between 0 and 15, and second indices is between 50 and 100, it means the curves are similar. So let's see in here. Sorry for that, but I don't know how to go away with this thing. So in here, curves are similar in this way. And see the results, F1 and F1, F and F2, or maybe in this way. This is the ankle joint. This is knee joint. This is ankle angle, knee angle, hip angle. Ankle torque, knee torque, and hip torque. Black line, dorsiflexor, and the dot line, red line is AFO. So you see in here, it should be also the normal result, but we can see that the curves started to be quite similar. Sorry for that. Here it's mistake. Black line is healthy person. Black line is healthy person. Okay, and dot line is AFO. Is AFO because if not, it will be without the sense. So we see that was the improvement. That was the improvement. And also in here, it was a healthy person and person with AFO. Healthy person and person with AFO. So if we compare the curves, it will appear that they are similar. If they are similar, it means that the orthosis improved the gait, that the orthosis improved the gait. The differences, the main differences, were not big because for the moments were mainly 0.8 in the press wing, and in here in the knee it was really good, so 0.3 of the difference between the curves. But from this let's say algorithm, it results that the curves are quite similar, which can follow us that this equipment works. And in this moment, I would like to go to balance. A few words about balance, because my next topic will be about gait perturbation. So before I will go to gait perturbation, I would like to say a few words about balance. So we will switch to the static position, but before we will switch. So maybe we will work in this way that I will finish whole my lecture, and after that you will ask me the questions. So for balance, we have to know a few concepts. So the most important concept is what is center of mass and what is center of gravity of an object. So center of mass is a position defined relative to an object or system of objects. It's the average position of all the parts of the system, weighted according to their mass. Center of gravity is a geometric property of an object. The center of gravity is the average location of the weighted of an object. So as you know, under Earth condition, those two terms are equal. So center of mass and center of gravity is the same point. And the location for human during standing is all the time anterior to the second sacral vertebra while we are standing in anatomical position. But of course, it's changed during the years. So if we have newborn, it results that the center of mass is above umbilicus. At the 2 years old child, the center of mass is at the level of umbilicus. After the child of 5 years old has to have the center of gravity below the level of umbilicus, and it still starts to go down until it starts to be at the level of second sacral vertebra. Of course, during standing. So we have to remember that composition of the body will play the main role in the location of center of gravity. So we also can imagine that if the person change its position, also the center of gravity will change the position. So we can find the position when the center of gravity is outside of the subject. If we will find this position, it will result that this position can be very difficult for example, elderly persons. And if yes, we have to be careful of them because they can fall down. So there is another concept, line of gravity. The line of gravity is vertical line which passes through the center of gravity. If this line fall on the base of support, the position is stable. But if doesn't, like in these two pictures, it means that the object is unstable and probably this person will fall down. And that's why, for example, this position that we want to take some object is not very good for elderly. They will come nearer to take this object because they will feel safer. So now we have to speak about what is balance and stability. Balance is the ability to maintain the body in equilibrium while static or dynamic. And stability is the ability of the body to return to equilibrium after being displaced. And the main factors which affect balance and which we can adduce is base of support. Because if our base of support is small, it will mean that it's very difficult for us to maintain the center of gravity in this base of support. If the base of support is large, probably the center of gravity will be also lower. And probably the line of gravity will pass through it and will line into the base of support. So to be stable, if we have the patient with some disease, they like to have some equipment which will help them to maintain the balance. Of course, it is the additional thing because normally we want to unload one leg or one limb which is with some, for example, fracture. And we have also a lot of factors which affect balance and stability. So we have two sets, physiological and anthropometrical factors. So if we look at our organism, it will result that we are never static. All the time we will have some small sways because the heart beat, because the blood have some circulation, because we breathe, because our central nervous system sends the information, because of visual system, because of muscle system. So all the time there are some sways. And the most important system that are responsible for the postural control is central nervous system, visual system, muscular skeletal system, and of course, vestibular and proprioceptive system. Vestibular system consists of three semicircular canals with otoliths, and its function is mainly correct position of the head in relation to the direction of the force of gravity. Visual system, the visual impulse runs along the optic nerve to the cortex, which has groups of neurons sensitive to vertical or horizontal orientation. And proprioceptive systems, receptor, which you can find in muscle tendons, will play very big role if we will think about deep feeling. So all these things, and also the anti-gravital muscles, will be responsible for postural control, for balance. So it's not so easy to assess it, and it's not so easy to maintain. And if we have a problem to maintain the stability, of course, we will use some strategy. And there are 4 of them. First strategy is ankle strategy. So this is the first strategy what we ever can see, especially when you will stay on one leg. The main activation of the muscles you will see around the ankle joint. And if yes, these muscles are very active. But if it doesn't work, the hip strategy would start to play main role. So those muscles around the hip joint will start to be very active. If still we have a problem, in this moment, the ankle and the hip muscles start to be acted together. So we can see that we will have combined strategy. And if nothing works, because remember that we cannot use the hands, in this moment, the step strategy appear. So to not fall down, we have to do the step. And in here, I would like to show you few nice movements. This is movements because balance we can assess during static conditions, so while standing, or during dynamic conditions by moving. And in here, you can see some nice motion. So base of support are the hands. And this big circle, white circle, is the center of mass of this person. So until this circle, center of mass, is in the base of support, this boy is stable. Next picture. The same in here in gymnast. Base of support is a bar. And here we have the center of mass of this person. And this is the motion captures analysis, and the red points are the centers of muscles of each segment. So this is the balance during dynamic, and you see few times that the center of mass is outside of this girl, outside in this moment it will be. Yeah, in this moment it was outside of this lady. And in here also another dynamic stability, of course using motion capture system, because it will be very difficult without it to assess. And the same explanation what I said, but this blue line is the center of pressure of the ball itself. So how to assess this complicated postural control, which is very complex? How to assess postural stability? Normally we use the plates. So we have two type of the plates. We have Biodex system, but in here I mean the plates which can have also the motion, so dynamic plates, because Biodex system in here we have a plate which can move. So we have a condition, static condition and dynamic. And of course we can use normal plates which can assess our body position during only standing. So in here, during measurements, you can see how many conditions we have. So we can assess the postural control, the stability during static or during dynamic condition. We can say that we have small or large base of support, so one leg standing or both legs standing. We can play with visual conditions, so one eyes open or eyes closed, stable or non-stable surface, dual task. Dual task is that, for example, while a person is standing, we start to ask this person about, for example, multiplication, or to answer where this person is living and so on, just to not make this person think about the measurements. Of course, fear. So if the measurement will be at the some level above of the ground, some persons can feel the fear. And virtual reality. So this is the picture with the foam on the plate. So we will have a unstable condition here. And this is Biodex system. Biodex system is very nice because you can use it also for the training, not only for the measurement. And in here you have a screen. This screen looks in this way. And this point on the bottom is your center of mass. And for example, you have to ask the person to go to play. So to go to on the right and on the left, or touch the balls which you see above on the slide. And what you have indexes, and which is very good. What we like in here, that the indexes what you have, they have standards for each age. So the protocol looks like here, and here we have indexes. So overall stability indexes, what I had before. Anterior, posterior, which is green, and yellow mediolateral daleks. And the triangles in here are your results, So if you are in the norm, it's okay, but sometimes the person fell outside of the norm, and it's the problem. So you, as a future physiotherapist, you will know that you have to work with this person, but probably first you have to know what's happened. Maybe this person didn't understand the equipment, because sometimes it's happened. So never ever take the first result. You have to be sure that this person understood the equipment, because sometimes there is a fear, sometimes there is a stress on equipment. So you have to be sure that the task was natural. If the task was done natural, you can take this result and you can detect why it was so wrong. What's happened? Maybe this person has a very weak muscles, so maybe this person needs to work with the muscles. Maybe there is problem in the brain, so you have to detect where is the problem. You will know that there is a problem from the equipment, but what to do with this problem and how to do, this is your job. This will be your job. And static condition, normally I didn't say to assess postural control stability during measurement. The trial, the test takes only 10 up to 30 seconds. The most often is 30 seconds. And you can, in here, you can play both leg standing, one leg standing, eyes open, eyes closed. This is the typical protocol. And here it's important what we will obtain, because during standing, we will have the center of pressure motion. This will be recorded. So the center of pressure is a point of application of ground traction force. We are standing on both legs, so it will be resultant ground traction force according to the third Newton law, action reaction. And what we obtain the center of pressure path length, which is, as you know, very, very irregular. So it will looks in this way. And probably, I don't know, because today I took this picture from internet. This is the center of pressure path. So probably this blue means that it was the young person, healthy person. And probably this red means that it was the person older, probably. I don't know, because I didn't read the paper. But why I think in this way? Because whole young persons are mainly sways anterior posterior. So in here I can detect that it was mainly healthy persons. And all elderly starting to sway mainly in mediolateral direction. So that's why I think that main difference between these persons was the age. Maybe I'm wrong, because this maybe it's, for example, some healthy person, this is some disease. I don't know, but this is the first view. And of course, here you have also the person during thinking. I mean that if we don't know something very well, we start to think, oh, I try to not move, I try to not fall, I try to do my best. And the result will be very good. But if you are concentrated in something else, for example, like dual task, your result can be in this way, so very bad. And why we can assess sways, movements of the body during standing using plate. Why? Well, it was some experiment when the one person recorded center of mass using motion capture system, and in the same time center of pressure using plates. And in here you see the results. So dot line is what we obtain from the plate, so center of pressure, and this line is the center of mass from motion capture system. And if we do minus, it will result that center of pressure signal minus center of mass signal, it will be around 0. So this will mean that that we can use plates to assess center, to assess body sway. So we have these parameters, so-called linear parameters, which can play the main role to assess postural stability. So the center of pressure path length, so is the basic indexes to assess. What is this? If you take this black line and you will open this line, the longer this line is, the worse stability was. So the person sways a lot during this task. And the same interpretation you can find for in other parameters. Now I would like to switch to another presentation, I mean to Gait analysis. So please give me a few seconds just to close in here. And I will go to another presentation, and after I think that you can give me the questions. Okay, I think that I am ready, so I will share the screens once again. Sure, and this presentation is quite short, so I hope that you will be able to listen to me a little bit longer. Maybe I will need half an hour or even less to speak about it, and I hope that it will combine all our knowledge. So now I will, as you see, first I spoke about the gait, very general informations. What I used after to description the persons with drop foot, their kinematics and kinetics parameters, and I passed through OpenSim, which gave you possibility to assess something what you cannot measure, because you cannot measure forces of muscle, of single muscle, you cannot. You can only assess the activity of the muscle, which is completely different thing, using EMG. After that, I started to compare the persons with drop foot with healthy persons, and we saw where are the differences and which muscle can compensate. So we understood that our body is a chain, and if happens something wrong in one segment or one joint, it will mean that our joints, that in other joints are can go in the wrong way if we look at the loading. After that, I switch very hard in the balance. In the balance, just to say you very general information, but why? Because now I will go to perturbations, and not simply perturbations during standing, but perturbations during walking. So I will show you how we identify the type of reaction strategy in response to anterior-posterior perturbations during pre-swing phase of gait. And here I have to say that I only chose this phase of the gait. I have perturbation also if in other phases, but it's not analyzed yet. So I have to say that the study about the type of reaction strategy in response to perturbation during gait is a new approach, what you can find in biomechanics. Gait perturbations are performed normally using very modern technology that allows you to define the initiation, the moment of the sleep. So, in introduction, the purpose of the study of this person, Joe and Lockhart, was to describe accidental false injuries. False indicates four incidents were calculated from years 2006 up to 2010. And this study indicated that over 65% of fall on the same level injuries resulted in 31 or more work days lost. The major source of injury was floor, walkways, or ground surface. And the most affected body parts were the lower extremities and the trunk. So, as you see from this introduction, that the fall on the same level is very dangerous. And that's why we would like to know how our body react on the perturbation. So the purpose of this study was to determine which gait parameters change significantly with respect to gait due to sleeping in the pre-swing phase. So pre-swing phase was on the end of the stance phase of the gait. What we did? Well, we had 21 women. This was the students of physical education in our university. This is the characteristic of this group. And on this subject, we put the markers, 25 reflective markers, according to the human body model used in MOTEC system, which I'll present in few seconds. So subjects were placed in the Gait Reality Time Analysis Interactive Laboratory to collect their kinematics data. And please see this system in this moment. So we use GRAIL system, Gait Reality Time Analysis Interactive Lab. The picture is in here. So this GRAIL is a total package solution for gait analysis and gait training. GRAIL use an instrumented dual belt treadmill, which is in here. This is this treadmill you can see in here. This is dual belt. What this means? That this belt can accelerate or decelerate not together. And a motion capture system. So additionally, we have with this equipment, motion capture system, usually it's Bicon, and synchronized virtual reality, like this, so like in cinema, you are like in cinema, of course something for your safe, so harness in here. So with this equipment, we put person to the virtual reality, and this is similar what we can do using Gray. Motec Gray. So you can play with the treadmill, you can have this virtual reality, and your imagination is that exactly you are in this world, that exactly it happen. Harness will save your body and will not allow you to fall down. So this is what you can see. So this equipment is very good for training, for improve. For let's say that for scientific analysis, it's not so easy because exporting the data, it takes a lot of time. So for researcher, it's not very good. Okay, and what we did. So I would like now to describe our protocol. So first, each person declared their dominant leg. So the dominant leg was that leg what they used to kick the ball. So each of these girls had a left leg as support leg. And therefore, while walking, 5 perturbations every 10 seconds was detected on the left belt of treadmill, and the perturbations was deceleration of the left belt of the treadmill at the toe off, so in here. So during walking, one belt decelerated. If you cannot imagine what's happened with this, you will see in the animation and in real time, but how we did it. So we set perturbations using the flow software. So this is the flow software. It's a system designed for the development and immersive virtual reality application. The key concept of the flow system is that the subject is regarded and the integral part of the real-time feedback loop. The flow is composed of some modules, some like resource, chance, editors, and data. In here, you can choose what you want and you play with these quadrants. You can connect them and do, for example, something like movie in which your patient will be. So you can give the patient, for example, some game, and you can choose the scene, for example, the wood or something else on the waves. So the person will be on the boat, and this person has to maintain his equilibrium. And therefore, our mock-up sitting was as follows. So we set intensity at 5. It was the biggest one. So the treadmill really stopped, really decelerate, even as you know, toe off and side, left side. And every 10 seconds, it was stopwatch to do this. So it was done automatically. And let's say one girl, you see, she didn't do it in a good way because all the time she grabbed the rim, but you can see her from the right side, from the left side. So this is right side. Your left side, it will be her right side. Your right side, it will be her left side, and in the middle. So in here, you can see also first time in my presentation, the motion capture analysis. And as you see, the person less clothes dresses the person has, better is, because the markers should be put on the body. Because if they are put on the dress, the marker will move. The marker will move, and we will not have good record. So you see what was the reaction? What was the reaction? Something like squat, that the leg was backward. And this data, this kinematics data, we put it into OpenSea. Why? Because I wanted to see it slower, because I thought that it will be easier to see how the person walk. And let's see, this is two different persons. There are two different persons. Oh, sorry for that. I would like to stop when the reaction will be. Oh, sorry, I started to play with this. I didn't want to do it. This is different view. Maybe it will be better in this moment. I try to not touch nothing. Sorry for that. I wanted to stop in the moment what was very important for me. Okay, I see that I have some technical issue, but I wanted to say that the reaction, why I put it here to persons. First, I wanted to show you that the group of these 21 ladies, they react very similar, in very similar way. So it's good, because if we have some thought of stimuli, some perturbation, and the reaction among 20 persons is similar, it probably means that the reaction through whole population will be similar. That's good, because we can prepare somehow our central nervous system to perturbation which can appear suddenly. And let's see what changed. So we had kinematics parameters, so angles for perturb and for non-perturb leg, and this was selected for analysis. And in here, we wanted to compare what's changed, why change, and how change. And for comparison, we chose in 3 phases of Gait. So in first 20 seconds, we chose minimum and maximum value. This is ankle, this is knee joint. On this example, I show what we did. So for knee joint, in this phase, we chose maximum and minimum peak. After, in second phase, so from 20 to 60% of Gait cycle, we chose also maximum and minimum, and the same from swing phase. Why we chose only these 3? Subjective, only subjective feeling, because somehow we have to compare the curves. And we had these peaks for ankle, for knee, and for hip angles. during this normal gait, during perturb gait, and response on perturbation. And we use Statistical to play with this data. So our data had normal distribution, what was very good, because we could use ANOVA to answer a question: are there statistical significant differences between extreme values in selected phases of gait cycle? So let's see our results. First, before I will go to results, I wanted to show you the curves. So this is walking without perturbation. So this is ankle, this is knee, and this is hip without perturbation. So this is the same like in per book, and we have this here. Here we have the mean, and this dot line is a standard deviation. So very nice. This is an action. I called it an action, but this means perturbation. So this is how gait cycle changed when we had this perturbation. This is the action. So we see that the curves start to be completely different. And in here, we can see the reaction. We can see the reaction. And let's go forward with our analysis. So in here, it's the ankle joint. Maybe in this way, ankle joint. Here we see, I have to say a few words how to read this, because I know that there are a lot of informations. So let's start from the right side, okay? Here, right side. This is action, which is in here. This is reaction, which is in here. This is gait, which is in here. And maximum peaks for this gait. So for the blue one was between 0 to 20 maximum peak. From next we have maximum peak between 20 and 60. So 20, 60, and maximum peak between 60 and 100. So we had 21 peaks because we had the group of 21 persons, and we combine. So we see that for peaks in the interval 0-20, we have significant differences between action and reaction, and between reaction and gait, where the action maximum peak was the highest in compared to reaction, and the reaction peak was highest in compared to gait. So we see significantly changes in perturb and non-perturb leg in reaction after this sleep was detected in compared to gait. So the maximum values of the peaks change. And the same we have in here. So for 20 to 60% of gait cycle. So you see that for ankle joint, we have a lot of changes. We have a lot of changes, and all the time, action and reaction, we have bigger values. And what about minimum peaks? Minimum peaks we can find in here. And action, reaction, the changes we had mostly in interval, in first interval, so in loading response and in the swing phase. For the knee, The same. Sorry, I don't know what to do with this, so it disturbed me. So in here we see that for knee also we have a lot of changes, and the same result for the hip. I go faster because I wanted just to show you how we compare. And here are the conclusions. The reaction of this type of perturbation is similar in most of the participants, what we know already. The response is a straight squat, what we saw on the video. External rotation at the hip joint, we didn't see it because I couldn't stop the video, but I say you that it was. And a change in trunk angle, I didn't show you because of time, but the trunk goes forward. And perturbation results in a longer gait cycle for both left and right side of the body because of the squat position, what we observed. There are significant statistical differences in kinematics parameters, so in angles, and this probably will change also the kinetics parameters. And we said that these results can be very useful because this can be control group. Of course, we need more person for the control group, but our next step is how react elder persons, and we did already the measurements, but we have to analyze them, so it is a huge work. So now it's the last part of our meeting. And last part of our meeting is how to compare the curves. If you will go to the science, now or later, you will ask this question. Like me, a few years ago, I wanted to compare the curves. If that time I will be so smart like I am now, my life will be easier. Really, but I wasn't. So now I give you my knowledge. Maybe you will use it someone if it will be necessary, but it's good to know. So in biomechanics, you have three possibility to compare the curves, the continuous curves. First is dynamic time warping, second, statistical parametric mapping, and third, parametrization. Already you saw parametrization, but I will repeat. Let's start from dynamic time wrapping. One thing, I have to say that every single thing in here is done in MATLAB, because in Excel, you will lose a lot of time to calculation. So if you don't know, if you don't want how to do it, just you need to find a person who will do it for you. Some who is in engineering, this is really not a huge job. This is very fast, so it doesn't take a lot of time. It's not very difficult. So how to compare the curve? Here you can see that there is a black and red curve. This is the knee angle during walking. And we see, they are similar, but how similar? How unsimilar? We would like to know. So let's go to dynamic time. Let's go to dynamic time wrapping. No, let's go to first statistical parametric mapping because it's easier. In here, sorry for that. Okay, now it's good. In here, we have groups of curves. This is typical gait, and this is hip joint. So we had, I don't remember maybe 20, maybe 30 persons. Here we have curves of them during normal typical gait. And here we have the same persons, but they walked with orthosis. So this is this side with orthosis, and this is hip joint, as you see. And orthosis, this was the orthosis. And it was blocked on 0 degree. And using statistical parametric mapping, we can compare these groups of curves with these groups of curves. And we obtain that differences are between 50% till maybe 90% of gait cycle, because this picture is not really good. But in MATLAB, you can have exactly good values. So this statistical parametric mapping use t-test from statistical to compare groups of the curves point by point, like in statistic t-test do it. And we will have statistical differences like let's say, like a range, right, an interval where these differences were. So let's go to dynamic time warping. I don't really like this method for only one reason. Why? Because it works in a little bit different way. This method compares the set of curves to one. And why I don't like this? Because you have to have this one, the best curve. So how do you know that this was the best one? I mean that in here, in statistical parametric mapping, you have group to group. And in here, you have to choose one, the best curve. And the way how you will choose it, it's not so clear, because of course you will say mean. And if you don't have normal distribution, maybe it should be median. So it's not so clear. And after, the comparison will be very similar, because you will compare curve to curve. This dynamic time warping do it. So if I have a healthy person, like in here on the left, this is Gait in Polish language. I didn't change, sorry for that. But this is Gait. So I said that this is the best curve from healthy persons in my lab. So I could compare healthy person to this curve. So I had the range in which this curve can go. So after to compare, for example, the curves from orthosis with this good, I had another range. And to compare, I had to do another statistics. So it was hard and not so clear, because as you see, dynamic time warping give you answer that you have, the curves are different. And you will ask me as a physiotherapist, okay, where? Because it's important for me. Because, for example, in mid-stance, I have different muscles working. And I said, sorry, but I don't know. And that's why I prefer statistical parametric mapping, because it will detect exactly where is the problem, where is the difference. And the last one is parametrization. You know it already, because in parametrization, I use it just in this work, because I said, oh, we chose maximum, minimum, and parametrization, it's that. So this is choosing the most characteristic points in the curves and make a comparison. This is parametrization, and this is what you will find in every biomechanics paper, most of the papers. Okay, I finished. Thank you so much. So if you have a question, please, I stop share the screen.
Excellent, exhaustive presentation. Very good presentation, Michalina. So, am I audible? No?
I have problem with the sound. No, it's not you. It's in here in this computer. Maybe I will close the video. Sorry for that. See, I have here some problem. I don't know what is this. Maybe.
To desktop 0.
Okay, now do you hear me now? Try to speak, please.
I do hear you.
Yeah, thank you. Okay, thank you. So I hope that you heard all my presentation, because
Yes,
I don't
yes.
know. Okay, so good.
I did. Yeah,
Okay.
Michalina, I have to compliment you for the patient's presentation, because it's been such a lengthy time that you have taken to explain from the very basics to the nuances that one should understand in the process of understanding the gait and while reading the gait related papers. So that's fantastic for your patients in first place. And depth of understanding, I really appreciate your depth of understanding, and it's really commendable when you're detailing to a novice person to understand the way they should look at the paper when they're reading on gait or any of these balance aspects. And especially like the way you have explained OpenSim to understand what it makes us to look at and how to interpret what it has given us. So that's fantastic again. And the MOTEC system.
Yeah, I hope that I was clear, because I understand that it is very difficult. It's really very difficult to understand, because I teach my students and I know that they have big problems to understand, to feel it, to be there. And I understand that maybe not everything was clear, but I can say that if you have some sense of this, and if you can see it as a one piece, it's good, because after small pieces were inside, you can add to your knowledge. But if you globally took this lecture, it's good. It's good. It's my aim.
True. That was good, actually, like the way you integrated the OpenSim, and how do you understand the dynamics out of that, and MOTEC system to challenge the balance, and integrating OpenSim and MOTEC system when you want to assess someone. So these are fantastic ways. And also to look at the analysis of data from parameterization to statistical parametric wrapping and dynamic time wrapping, which is most commonly used. Why is parameterization so commonly used, and why is it that statistical parametric wrapping is more preferred when compared to dynamic time wrapping? The explanations that you have given are very reasonable for a physio when they're reading the paper to understand which method they have used and summarize the data.
Yes.
Yeah. So, we have certain doubts, rather the questions for you. So I'm sure that they are very simple at your context. So to start with, there is a question in the chat posted by one of the participants. Balance and postural stability are two terms that are commonly used interchangeably. Yeah.
What is the difference between postural stability and balance?
And in an analysis perspective, so how do you
I
differ?
will, yeah, that in the papers, normally these two things goes together. But in physiotherapy, having the classes in Erasmus, I understood that you understand postural stability as the proper posture, so working of the muscles that, for example, keep your spine in good position. And balance, it will be equilibrium. So here we speak about postural control. So how to keep our posture good and not fall down. Because if you change postural stability, you can fall down also. So I had, if I can share the screen once again, I had the definition there. So I go there. 1 second, share the screen, and it should be here. So I will do this lecture. And I will try to find this slide because it will be on the end. And there was the definition, balance, yes, balance stability. Balance is the ability to maintain the body in equilibrium while static and dynamic. Stability is the ability of the body to return to the equilibrium. So in here, you will use whole masses, but also in here. So going here in biomechanics, in this biomechanics, what I present, you will not see the differences between those two things. Yeah.
Got it. I hope the person who had asked got the answer too.
Yeah.
Fine.
But as I said before, in the physiotherapy, postural stability you will define as a good posture. In biomechanics, it will be for us the same. And that's why I had the problem with the students for Turkey, because they came and they thought that I will have the corrective exercises with them. And it was not this. Yeah, it was misunderstanding, yeah.
Fine. So there was one more question that was there in the question and answer session. The question is about how are normalized values of center of pressure during gait being generated, and are there any normal references that we can say based on which the gait center of pressure excursions are normal or abnormal?
So center of pressure, path length, I don't know if I understood in good way. So if you have center of pressure, you do not normalize it because it's a point which moves. So you don't normalize. This point moves and you will have some path length, and it will normally be in millimeters. So the longer is this path, the more sway you had. The shorter, less sway you had. What you normalize, normally, you normalize the values of ground reaction forces. So if you have ground reaction force, you have in newtons. But to compare the persons, you have to normalize divided by the mass. And your result will be Newton divided by kilogram. So force divided by mass. And this is normalizing on ground reaction force. And the same you do with the torques. And it will be torque, the unit is Newton on meter or Newton on millimeter. And you normalize by kilograms, so by mass, so it will be Newton on meter per kilogram. Center of pressure, you don't normalize because if you I had the slides where I saw, and once again, I need to share the screen. I had this slide before, sorry for that. This is long presentation, that's why I have so many.
True, true. It was in the initial phases of the presentation.
Yes, yes. Oh, here. This is the maybe here. This is the center of pressure point, how it moves along the foot. And in here, you see the pressure. The pressure will be in Pascal. So it's the area which is the most loaded in red. And here it's the area the less loaded. And these points in black, they are the resultant points of these areas, and you don't normalize it. You don't normalize because this has the areas are in Pascal, and the points, it's only the point where the resultant ground reaction force was applied. And that's all. That's all. So it's Pascal, and that's all. Yeah.
Good. There was one more question. Like most of the times we get to see that lots of analysis and biomechanics studies are carried out on sports individuals. The ones who are athletes, who are elite athletes, who have an injury and are willing to get back to their sport following the injury or after rehabilitation. And physios sort on the gait and kinesiological analysis and biomechanical analysis. So how directly is it really like useful towards the end, and how was those interpretations made from the analysis?
Do I understand? Because not all I understood. So I would like to be sure if I understand in good way. The question is, how can we improve the sports?
Yeah.
How we can improve technique? Okay, so normally we have two ways. The old way for improving, which is not already valid. I tell you why, but I tell you the way. It's you have the champion, the best, for example, in the world or in the nation or in the team. You have this best person. So you take the parameters of this person during motion by motion capture. And after that, you ask the beginners or another person from the group to do the same, and you can compare. And why it doesn't work at all? Because of our different structure. I have different body than my colleague who do the same sport. So, and maybe I have different range of motion. So maybe it will be impossible for me to do exactly the same thing. So this is not good anymore. This is the old what we did, and still already at some point is good, because if we have beginners, we can do it if you are not at extremes of the sports. But what we do, we started to count energy, because if you don't lose a lot of energy during some motion, it means that this motion was effective, economic. So we calculated it for short put, and techniques was different because you had Gait, you have rotational, and it was result that our champions, because it was Polish national teams, they are different due to energy. And it was result that these best had lost a little energy during this task. And those a little bit worse, they lost very good amount of energy. So maybe energy will be good to compare. But I mean that sport is very individual. So you have to look at the person individually and look at them, because also, as you know, in sport, very important is what you have in your head. So now it is holistic thing to join the sport. So very good athletes has psychology, massage, this, that, and whole company who follow this person. Yeah, but from Gait, from motion capture, you will obtain main parameters and you can play with them along the body of this person will allow you. This is also your intuition as future trainer, if you can do it or not. Maybe this person is not able to do it, so you can fit. Yeah, and I know that, for example, along the child's arm, you can look at the child and you say, oh, maybe you will be good at running because you have long Achilles tendons or something. So I know that they started, the science goes also in this direction. Yeah. Microphone, you need the microphone.
Yeah. So, Michalina, I have one doubt. Always in the papers that we read on dominant leg and non-dominant leg, yeah, almost all the authors try to define operationally what is dominant and what is non-dominant based on the sport that they want to analyze. Say, in your presentations, you have consistently used the kicking leg as the dominant leg, whereas lower quarter function is to weight bear and a stable weight bearing platform, to provide a stable weight bearing platform for the whole body. So if I say the stance leg is the dominant leg when the non-dominant leg is swinging, so is that okay to accept that?
I had this problem during a review of one paper. When I wrote that dominant leg was right leg because they kicked, and sorry, to not be confused, because I thought that the leg on which I am standing normally is the dominant, because it will be stronger. So if I kick the ball, this is the leg what I use. So I thought that my dominant leg will be left. Okay, I hope that I don't confuse, because I kick leg with right leg. I kick ball using right leg. So I am standing on left leg, and I thought that my dominant leg is left because it is stronger, because it is my supportive leg. And in the review of the paper, the reviewer said that I am wrong. And he gave me a paper, and when the paper explained that the dominant limb is that what you use for writing, kicking, this is your dominant limb. So in here, I have right limb dominant because I use it for writing. I have right leg dominant because I use it as kicking. So this is from the literature, and I know that I was good because someone, you know.
True. I have a doubt. Didn't you try to go ahead to clarify this by looking at probably the forces that the dominant leg, the stance leg in this case, or the swinging leg in another case?
Stance leg is not dominant.
Yeah. So for
Yeah.
now, probably like after you explain,
Undominant.
Non-dominant and the dominant. What is the difference between them through the activities? Are they different with respect to the amount of force production or being economical?
The aspect is that you are right, that if I really want to do difficult task from that person, I should alter the right leg because
True.
it will be difficult for them. But why I didn't do it? Because we will have persons 60 years old and we was afraid about it.
True.
And that's why, and this young person should be controlled. So that's why we set the experiment in this way. But it was the discussion. And you are right. Yes, you are right. Yeah.
So I think that can be a good study, like where you can think about how should we go by someone's paper saying as it is defined so, or what does the science actually say with respect to the parameters?
Yeah, but I mean that your suggestion is good because we can ask one more time the students to come and we will alter right leg and we will see if the results, if the answer is the same.
True.
Good, thank you. Now I have another job.
A good session. I think we don't have any more questions waiting for you to be answered. And thanks for patiently and answering the questions and detailing the answers as well. And it was a fantastic session overall. I'm sure that all of the members who have participated would have gained significant insights into the way we should look at the papers. Because in India, in normal convention, when we say recent advance, some of us may expect only the last few papers that are published in the last few years may be analyzed to summarize. But actually, you give the insight to summarize any paper that is going to get published in using these systems. That's fantastic.
I think that I see that you are on the beginning, and me some years ago I was on the same point. And I mean, this is fast. Now this is really fast. If you have equipment, you will see that if you will have new lab, new equipment, it will go forward because you have good team, you have good staff, and it will really go forward. And me, in my lab, I am alone. So it is very difficult for me to join everything. Because of time, simply because of time. But yeah, I mean that if I saw more than 60 persons once, and I think that maybe if half of them will be really interesting in biomechanics, it will be huge lab. It will be huge lab at huge knowledge. And as you know, I am open to collaboration because it's good for you, good for me. And I think that it will work. It will work. And yeah. And as I said to you yesterday, you are one because you have hospital.
Very nice interacting with you, Michalina, and nice to have you on our campus. And even though it's a short visit of 1 week, it's really insightful discussions that we're having. So probably for time being, for today, we'll conclude this session. And thanks a lot for all the participants for being there and patiently listening through all the presentation. I think I can say 95% of the participants listened through complete presentation. And definitely the next paper that we're going to read on biomechanics is going to be much easier to understand. Thanks a lot for that, Michalina.
Thank you. Thank you.
I think we can conclude the session as there are no further questions. Thank you.
Thank you. Can I leave? Yes.
Yes.